Okay, so we learned about logarithms last time. Now there are more properties of logarithms to cover today. So in the properties given next, m, n, and a are positive real numbers, and the base of a cannot be equal to 1, and r is any real number. So we're just saying that whatever we are applying to these logs, they must be positive real numbers, and the log base can never be equal to 1. Has to be greater than 0, but can't be equal to 1. Okay, so our first log property says log base a of 1 is equal to 0, and the natural log of 1 is equal to 0. So no matter what the log base is, the log of 1 will always be 0. And that goes for the natural log as well. I could say log base 5 of 1, and the result would still be 0. So the log of 1 is always 0. Okay. We'll put numbers on these. Why not? 1. And then 2. Log base a of a is 1, and the natural log base c of e is 1. Okay. So property 2 says that if the log base is identical to the value inside the log, then they will cancel and give you 1. And the same goes for the natural log of e of 1. So we know that the base of the natural log is e. We don't have to write it, but since that base is there, the base is the same as the number inside the log, then it will cancel and give you 1. And of course, the reason for these values is because of the exponential rules as well. Let's say that we wanted to convert one of these to exponential. Let's say we convert the natural log. If I converted this, it would be e to the first power, and you would set it equal to the inside of e. Well, it just so happens that e to the first is e, so it all checks out. We could even do the same for the log in the first problem. If I converted this from log to exponential, well, a to the 0th power is equal to 1. And we know that anything to the 0th power is 1. So remember, since they're inverses, we now can say that the log of 1 is 0. So these are where these properties come from. Okay. I guess a good example of this, let's say I had log base 6 of 6. Since the base is the same as the number inside, we would get 1. Okay. 3. A raised to the log base a of m is equal to m. So now if you have an exponential function being raised to the power of a log, if their bases are the same, then they will cancel and leave you with the value that's inside the log of m. So a raised to the log base a of m is m. And the same goes for the natural log. E raised to the natural log of m is also m. Okay, good example of that. Let's say we did 2 raised to the log base 2 of 5. Well, these bases match. They would cancel each other and just leave you with 5. Okay. 4. Log base a of a to the r is equal to r. So this one, again, is a consequence of number 2. So here, your log bases are the same. Well, the base is the same as the number inside the log. So they will cancel and leave you with the exponent of r. And the same, again, goes for the natural log. Okay. And another good example of that, let's just say we had log of 10 to the r. Well, this is the common log, so the base is understood to be 10. Since these bases match up, they will cancel and leave you with r. All right. So those are some fun log properties. More to go. Okay. Next are the I call these the three most important log properties because they will help you survive in Calculus 1 and most likely Calculus 2. So the first property is the product to sum rule. So if you have the log base a of m times n, then you can take the product that's inside the log and split it into multiple logs by addition to the sum of multiple logs. So log base a of m times n becomes log base a of m plus log base a of n. If there were multiple terms inside the log, then you would keep expanding. If there was 3 terms, you'd have 3 logs, 4 terms, 4 logs, so on and so forth. And the properties hold the same for the natural log. The natural log of m times n is the natural log of m plus the natural log of m. And what's cool about these properties is you can reverse engineer them. You can take the sum of multiple logs and you can rewrite it back as the product of one single log. Okay. So that is the product to sum, and we could even say sum to product. All right. I guess I give examples for most of these, right? Why not? So a good example of these, let's say I had log base 5 of x, y, z. There are 3 terms inside the log, held together by multiplication. We can expand this to log base 5 of x plus log base 5 of y plus log base 5 of z. There you go. That's how that property works. And if I wanted, I could put all these logs back into one single logarithm. Okay. Then next property is the quotient to difference rule. So if I have a quotient inside my log, then I can write it as a difference. Okay, so log base a of m over n can be rewritten as log base a of m minus log base a of n. Same goes for the natural log. Natural log of m over n can be rewritten as natural log of m minus natural log n. All right, good property. Let's try the natural log this time. Let's say I had natural log x plus 1 over x minus 2. I could rewrite this as natural log x plus 1 minus natural log x minus 2. Okay. And then 3, the power rule for logarithms. This one's the easiest. If you have log base a of m to the r, then by the power rule for logs, all you do is you take this exponent and bring it to the front. And then you have r times the log base a of m. Okay. Same goes for the natural log. If you have natural log of m to the r, once again, that r, that power comes down, and you have r times the natural log of m. That is the power rule for logs. So good example of that. Let's say I had the log of x to the 5th. Put that in parentheses. I could rewrite this as 5 times the log of x. There you go. And the same would go for the natural log. All right. So those are some log properties. But definitely remember these 3. they are lifesavers. Isn't that right, Carl?
It's beyond right.
Yeah.
Beyond right. So
Beyond.
save your life in calculus, Cal 2, Cal 3 if you're expeditious, differential equations.
There you go. They take complicated problems and make them simpler. So just saying, don't forget those three. Okay. Let's go ahead and do some practice with the rules we just learned above. Use log properties to find the exact value of each expression. So we have log base 2 of 2 to the negative 13. The base of the log is same as the number inside the log. These will cancel and leave you with just negative 13. But even better, this is how crazy logs are. We could even use power rule on this log, and you would get negative 13 times log base 2 of 2, and log base 2 of 2 is 1, and you'd get negative 13 times 1, which is still negative 13. Love it. Gotta love logarithms. Just as crazy as exponentials. Okay. B, the natural log of e to the square root of 2. So for this one, well, it's just like A, like the problem above it. We know the base of the natural log is e. So these two match up. The base of the log is the same as the base or the number inside the log. So those will cancel and leave you with the square root of 2. And again, you could also use power rule on this one, just like we did above. You could say, all right, the square root of 2 comes down, and you get times the natural log of e, and the natural log of e is 1. You get the square root of 2 times 1, which back there. Good times, fun times. All right. C, e raised to the natural log of 8. So this also follows another property that we saw on the first page. The base of the natural log is e. These bases match up, and this will just leave us with 8. There you go. Yeah, I don't think there's any other way to show that one. Or there could be if we set it equal to y and drug it out, but just trust that. Okay. D, log base 6 of 9 plus log base 6 of 4. So they're giving us the sum of two logs. And what we notice is that these logs have the same base of 6. So with the three important properties that we showed in the last page, we can take the sum of two logs that have the same base and rewrite them as a single log with the product inside. So this will become log base 6 of 9 times 4. So we have just reversed the product to sum. We went sum to product, and now we're going to get the log base 6 of 36. Oh, but we're not done. 36 can be rewritten as a base of 6. So you get log base 6 of 6 squared. Now we have that property where the base of the log matches the number inside the log. They will cancel and leave us with 2. Crazy, crazy. Okay. E, log base 8 of 16 minus log base 8 of 2. So now we see we have two logs held together by subtraction. So we can now use the quotient to difference formula, but backwards, because we're going to put them together as a single log. So log base 8 of 16, these have the same log base. So we can put these back as log base 8 of 16 over 2. Log base 8 of 16 over 2. Okay. Well, we know that 16 over 2 reduces to 8. And look what we have again. Log base 8 matches 8. And we know that this will cancel to 1. All right. And F. 5 raised to the log base 5 of 6 plus log base 5 of 7. So to clean up this expression, we're going to have to combine these two logs into one single log. Well, they have the same base of 5. So this will become 5 raised to the log base 5. So they have the same base. They're held together by addition. So we're going to put them back together as a product. So you're going to get log base 5 of 6 times 7. This will give us 5 to the log base 5 of 42. Now, this base of 5 and that log base of 5, they are the same, they are equal, they will cancel, and they will leave you with just the value inside the log, which is 42. Yeehaw. All right. Any questions on that page? All right. Got some log masters. Okay. So now for the next examples, we're going to take each of the log expressions and write them as a sum or difference of logarithms. So we're going to expand them by those three important rules on the first page. Okay. So A, you have log base 3 of x over 9. So we see that there is a difference, not a difference, sorry. I'm already giving it away. There is a quotient inside our log. So we can rewrite this as log base 3 of x minus log base 3 of 9. Okay. So this would be done, but we see that we can keep going because 9 can be written as a base of 3. So this can become log base 3 of x minus log base 3 of 3 squared. And once again, this will stay the same, but over here, these bases are the same. So they will cancel, and we'll just be left with that exponent of 2. All good? Okay. B, log base 7 of x to the 5th. For this one, all we're going to use is power rule. So this 5 is coming to the front. So we will end up with 5 times log base 7 of x. And there's nothing else we can do there.
You don't want to split it down into log 7x 5 times? Or
No. No.
I mean, that's what the directions say.
How dare you? Like log 7 plus log 7 plus log 7.
Yeah.
As a sum or difference. That is true. As a sum or difference. Whatever, Carl. Okay.
I'm not saying to do that. It's a joke. It's a joke.
I'm
It's too much.
pretty sure it's just you and me in here. So it's cool.
Seems like it.
All right. You got natural log of e over x. So again, you have a quotient. So we're going to go quotient to difference. So we're going to rewrite this as the natural log of e minus the natural log of x. And again, we can keep going because we learned that on the first page, the natural log of v is equal to 1. So you get 1 minus the natural log of x. Yeehaw. Okay. Again. D. Log base 2 of a over b squared. So again, there's a keep saying different. There's a quotient inside your log. So we can write it as a difference. And you'll get log base 2 of a minus log base 2 of b squared. Okay. And now we're almost done, but we can clean this log up one more time. We can get this power down by using the power rule. So you'll get log base 2 of a minus 2 log base 2 of b. Done and done. All right. Any questions so far before we keep going? Is that a no? Oh boy. Okay. Let's keep moving. E. Log base a of x times the square root of x squared plus 1. This little restriction here is just telling us that whatever we end up with, all your x values must be greater than 0. I guess that even works for this now because you can't plug anything negative, or you can't take the negative of a logarithm. Did I say that backwards? You can't take the log of a negative number. Okay. So for this log, we see that there are 2 terms inside connected by multiplication. So if we expand this, you'll get log base a of x plus log base a of the square root of x squared plus 1. Okay. Well, we have some cleaning up to do. The log base a of x is fine by itself, but we can rewrite that square root as x squared plus 1 to the 1/2. And then all we have left to do is power rule. We can bring that 1/2 down and we'll be done. We get log base A of x plus 1/2 log base A of x squared plus 1. There's
And I don't
nothing
know.
else we can do.
I don't know how many problems I did in Diffie Q1 that end up looking like this towards the end. And if you can't do this kind of stuff, it's like impossible to simplify them enough. But if you can just, you got these things on lock, it's so easy. This is like, I'm just staring at the, like the last few steps of every Diffie Q problem I ever did.
See? Logs make your life easier, guys. Okay. Dun, dun, dun. All right. F. You have the natural log of x squared minus x minus 2 over x plus 4 squared to the 1/3. And our domain has to be any x value greater than 2. Okay. So let's go ahead and expand this. But the first thing that comes down is that 1/3. So we're going to get 1/3 times the natural log of x squared minus x minus 2 over x plus 4 squared. Okay. And now, since we brought that power down, we can now expand the inside. The inside is a quotient, and we'll write it as a difference. So you will get 1/3 times, I'm going to put a bracket here to be neat, the natural log of x squared minus x minus 2 minus the natural log of x plus 4 squared. Okay. So again, almost there, but now we can do the power rule on this exponent, but for this log, this is going to have to be factored. So we're going to get 1/3 times the natural log of x minus 2 times x plus 1 minus 2 times the natural log of x plus 4. All right, almost there. Because now, since we factor that, we now have to expand this logarithm by the product to sum rule. So we're going to get 1/3 times the natural log of x minus 2 plus the natural log of x plus 1 minus 2 times the natural log of x plus 4. And now this is completely expanded. We can't expand it anymore. All we have left to do is distribute that 1/3. Sure, why not? I don't think we have to, but let's do it anyways. 1/3 times the natural log of x minus 2 plus 1/3 times the natural log of x plus 1 minus 2/3 times the natural log of x plus 4. There we go. Okay. And that is how you expand those logs using the 3 main log properties, and of course, some of the other ones we have learned so far. Okay. Anybody have questions on this page? Or is everybody good? Send me a thumbs up or something. There you go. Look at that. Thumbs up. Perfect. Laughing face. There's people alive out there, Carl.
As long as it's one,
Yeah.
I'll take the one for the team. That's not the saying, but I'm gonna make that the saying.
Right. Woo, party. Look, I did party.
Hell yeah.
Ooh. Well, if you want, Carl,
Okay.
you want to reverse engineer them?
Heck yeah.
Cool. All right. Let's get you on there.
Show 'em long drawn out process that I used to go through as a student. I'm sure all my papers you look at, you could probably skip the first 20 things I wrote every time.
Bang. There we go.
Okay. Let's see. Share this. The whole screen. Cool. Yeah.
Woo.
Minimize that. All right. We're at 6.5. Is this it?
Yeah. 6.5.
Yeah,
There you
boy.
go.
All right. Cool. So I usually get a little confused. I wouldn't say usually, but sometimes I get a little confused when I try to do these sorts of problems. So what I always try to remind myself is that you almost want to do um, PIMDOS to try to get things back together, but you kind of want to go left to right with how you do this, right? Um, no, because that one won't work with this one. So that's what I'm talking about. Well, let me just write the stuff out here. So I always write my rules down before I use any of them, right? So what I'm noticing here is I'm going to have n log b of a is equal to log base b of a raised to the n power. And then I also have log m of a minus log m of b will equal log base m of a divide b, right? So I'm going to put these two together to do this. 2 log 3 of u minus log 3 of v will equal log 3u squared minus log 3v, and that will equal log 3 of u squared divide v. And you're done. I won't write this anymore for the rest of these that I do, but I would highly recommend doing it like this. This is the way that I did all of my own homework and all of my own studying when I took this class, and it's still how I do this when I take classes still. And it eats up time, but it lets you combine studying and homework like into the same process. And then when you get to the exam, like if you all this stuff memorized just because you've beat it into your head by doing it this way, it's just one less thing for you to mess up on the exam. All right, so the next one we want to combine these down into one, right? So we have addition with similar bases. That means that this will be equal to log base 2 of the quantity 1 over x divide 1 over x squared. All right, well, what is that? Just 1 over x, but we'll figure it out. So as side work, we have 1 over x divided by 1 over x squared. This is equal to 1 over x times x squared over 1. This cancels. This goes to 1. So we are left with x over 1, which is just x. So this is equal to then log 2 of x.
Wait, Carl. You're
What's up?
supposed to multiply them.
Yeah, I was about to say you're doing
Oh
a
yeah.
quotient.
Okay. Never mind. Never mind. It's late for my old man brain, I guess. I don't know.
It's Monday.
You know what it was? It's because I saw the fractions and my brain's like, fractions
Yeah.
is just division. All right, so then this is 1 over x times 1 over x squared. And we can do the side work for this too. This is 1 over x cubed, right? So this is going to be log 2 of 1 divide x cubed. I'm going to rewrite this as log base 2 of negative, or sorry, get ahead of myself, x to the negative 3 power, right? So then this will be negative 3 log base 2 of x. All right. Cool. Keep switching colors all on down the list. Okay. So I guess this is the thing I was talking about that I kind of get confused about here. So I know from having done this quite a few times now, just practicing these, that if I don't take this and put it here first before I do anything else, this whole thing will be wrong. So anytime that you see some kind of number out front, a multiple of something, make sure you convert that to a power using the power rule before you do anything else. Okay. So we will get that this is equal to log of x squared plus 3x plus 2. And this will be minus log of x plus 1 squared. And then this is going to be equal to log of the whole quantity, x squared plus 3x plus 2 divided by x plus 1 squared. And then this top part here can be rewritten. We'll have the log of, this will be what, x plus 2, x plus 1? Yep. Divided by x plus 1 squared. This cancels to 1, that cancels to 1. So this will be equal to just log of x plus 2 divided by x plus 1. All right. Any questions so far before I keep moving? Gotta know. All right. I'm assuming that speaks for everybody.
Yeah.
Okay. So again, first things first, move these up with the power rule before you do anything else. So we'll get log of x cubed plus 1 to the 1/3 power plus log of x squared plus 1 to the 1/2 power. And then we'll use our addition rule. So we have log of the whole quantity, x cubed plus 1 to the 1/3 power times x squared plus 1 to the 1/2 power. Oh boy.
I think, yeah, that's it.
Yeah, that's pretty much it. There's really no easy way to combine these down. All right, move on to the next one. Let's do it in orange. Okay, so move all the powers first. So we get log 5 of 3x plus 1 cubed minus log 5 of 2x minus 1 squared minus log 5 of x. Now, this is another one where you want to pay attention to your order, right? So when you have multiples of these together like this, it'll work out the same way if you're very careful about it, but I have personally found it's easier to think about these almost by going in reverse and dividing these as one step, and then dividing them against this one as one step to take them back together. So let me show you that step by step. This will be log 5 of 3x plus 1 cubed minus log 5 of the quantity 2x minus 1 squared divided by x. So then this is equal to log 5 of the quantity 3x plus 1 cubed divided by 2x plus 1 squared divided by x. And then from here, we'll work out the side work. And I don't know why it works out this way better for me to think about it as like going from right to left. But for whatever reason, I remember when I took this class and some classes afterwards, when I would try to go do everything right or left to right, like when you expand them, I would make more mistakes. And this is the way that I've done it since then. And I just make fewer mistakes doing it this way. I don't know why that works out, but if you catch yourself making a lot of mistakes, maybe try doing it this way.
He's trying to get your attention.
-1, not +1. It is -1. Gotcha. Okay, I see what you're saying. Yeah, that would be oh, that's fine. I'll just rewrite it. That would be catastrophic, wouldn't it? -1.
It wouldn't be too bad.
Okay, so let's do our side work, right? And throw that back in there. So this is, we're starting with 3x plus 1 cubed over 1 divide 2x minus 1 squared over x. So this is, oh man, 3x plus 1 cubed times x over 2x minus 1 squared. Okay, so this is x times 3x plus 1 cubed divide 2x minus 1 squared. So let's work out our numerator and our denominator first. So numerator. We'll make this x times the quantity. If we FOIL this in our heads, right? I can just do this in our heads real quick, but I'll walk you through it out loud. We have 3x times 3x is 9x squared plus 3x times 1 is 3x plus another 3x times 1 is 3x. So this will be plus 6x plus 1 times 1 is 1.
Wait,
and then this will be...
I don't think you have to FOIL it all out.
No,
right?
I mean, okay. I don't... If you're fine with Leah, I was just going to simplify it.
You can leave it like that. Yeah.
Okay, then we'll just erase this and
I was like, wait. It's done.
It's done. I'm just saying, maybe you'll be able to find something simpler. So anyway, this is going to be our last step then. So we'll have log 5 of the quantity x times, just kidding, 3x plus 1 cubed divided by 2x minus 1 squared. All right. I forgot Professor Carrillo's nice and doesn't make you guys simplify every single thing.
Yeah, that would be crazy.
Oh, it's not that bad. I could probably do that in my head with a lot of mistakes. I say in my head, mostly in my head pretty quick, but also, I've been doing this for almost 4 years. So do you want me to keep going?
No, I got it. I'll jump back on. We can come back on the other page where we get real crazy.
Yeah.
All
right. It would be my personal recommendation. I know no one will take this, but my personal recommendation would be to try to work problems out where you do all the crazy work and try to simplify everything, because the hard part of calculus is going to be the algebra. The hard part of diff-EQ is going to be the algebra. So if you want to be an engineer or a computer scientist and you have to take DiffEq or linear algebra and stuff like that, the hard part that eats you alive is always the algebra. So get good at algebra now.
That's correct. Algebra, algebra, algebra. All right. So, hang on. I lost my windows. There we go. Okay. So here we want to approximate the log base 2 of 7. Well, if you have an old school calculator, you can't type in log bases. So we have to figure this out another way. Okay. Okay. Yeah. 4 plus 1 is 6. In Seattle, that'd be correct.
What does it even mean?
All right. So what we learned last time is to solve a log expression, you set the log equal to y. So we're going to set log base 2 of 7 or equal to y or x, whatever variable you choose. Why not do y this time? And then you convert from log to exponential. So this will become 2 to the y equal to 7. Okay. But now we realize that we can't break 7 down into a base of 2 to use the exponential equality property. So what we have to do now is apply logs to both sides of this equation. So we're going to apply logs to both sides. So I'm going to say log of 2y equal to log of 7. Oop. And now, by log properties we have just learned, we can use the power rule on the left side, where that y is going to come to the front. So we will end up with y times the log of 2 equal to the log of 7. And now, in order to solve for y, you'll divide by the log of 2, and y is going to equal log 7 over log 2. And if you didn't apply logs to both sides, if you applied the natural log to both sides, it would work the same way. So an equivalent expression is the natural log of 7 over the natural log of 2 is equivalent. And it said approximate our answer. So I'll do this to 3 decimal places. If I do log of 7 divide log of 2, we'll get 2.807. Now, if you have one of those TI 5000s, then yes, you can type in a log base and life is good. Or even on Desmos, you could do it. But if you don't, then this is going to be called, or you can use this process, which is summarized as the change of base formula. So if you're ever given log base A of m and you're told to approximate the value, well, we know that you can change the log base A of m into the log of m over the log of a, or equivalently, the natural log of m over the natural log of a, and you'll get the same exact answer. So we have proven the actual change of base formula by what we've done above. So this is another way to approximate logs. So let's go ahead and try it out below. And here, I'll even pull up Desmos. Hide this, hide that, hide this. Boom, boom. And this says approximate log base 5 of 89. Well, we know that we can rewrite it as the log of 89 over the log of 5. And over here, I'll type the same. Log of 89 over the log of 5. And we get 2.789. There you go. Okay. Next, do the same exact thing. Log base square root of 2 of the square root of 5. Rewrite it. You get log of the square root of 5 over the log of square root of 2. But before I punch this in a calculator, let's go ahead and simplify this more. We know that the square root can be rewritten as 5 to the 1/2 over the log of 2 to the 1/2. And now we know that by power rule, these powers can come to the front of the log. And we'll get 1/2 log 5 over 1/2 log 2, where your 1/2s will cancel. And all we have to type in the calculator is log 5 over log 2. And we get 2.322. Which would be the same result if we typed it in as log square root of 5 over log square root of 2. Same thing, 2.322. But what's the fun in that? Oh, here's where we start getting a little crazy. All right. This says to simplify. I don't think I need the calculator anymore. Okay. 3. Simplify log base 3 of 8 times log base 8 of 9. So what we're going to do is, of course, apply change of base. So log base 3 of 8 will become log of 8 over log of 3 times log base 8 of 9 becomes log of 9 over log of 8, where your log of 8s will cancel. And now we are left with log of 9 over log of 3. Okay, well, we can rewrite 9 as a base of 3. So you can make this log base, log of 3 squared over log of 3. And by power rule, that 2 will come to the front, and you'll get 2 log of 3 over log 3, and cancel. And all we are left with is 2. Wow. Or, there's that or route, right? You can reverse engineer the change of base. You can rewrite this as log base 3 of 9 which can be rewritten as log base 3 of 3 squared, which will still give you 2. Oh, it's just so rewarding. All right. Again. 4. Simplify e raised to the log base e squared of 16. Oof, we got some cleaning up to do. So we're going to focus on the exponent first. So you're going to get e, and what we're going to do here is change a base. So you're going to get log 16 over log of e squared. Okay. Clean up. You get e, and 16 we can actually write as a base of 2. But do I need to rewrite 16? No, I'm not going to do that yet. We're going to leave it alone. That'll come in later. You'll get log of 16, but then I'm going to use power rule on the bottom log. So you'll get 2 log of e. Okay. And now what we can do is take out this fraction of 1/2, which is there when we put out the 2, and you'll get e to the 1/2 times log 16 over log e. And now we are going to do the reverse change of base on this log fraction. So this will now become e to the 1/2 times log base e of 16. Reverse. And then we are going to reverse power rule. This 1/2 is coming on the 16. So you're going to get e to the log base e of 16 to the 1/2. And now the magic happens. This base of e and that base of e are exactly the same. They will cancel and leave you with 16 to the 1/2, which is the same as the square root of 16, which is the same as 4. Yee-haw. I told you. It gets crazy. Okay, so that is change of base. Anybody have questions on that? They're like, not anymore. Not after that one.
That's a lot of stuff.
We didn't do much. I just used all the properties we learned today.
That's a lot.
All right. Well, now we get to have fun because this page is called Being Real Extra with Logarithms. All right. You want to have fun with this page, Carl?
Sure.
Yeah. It's a good time.
Right. Let me go load it up again.
Share.
Roll to the bottom. I want to show everybody my Discord. Share it up. Yeah. You guys see that?
Yep.
Gotta get back to it.
Loading.
All right.
5 days later.
3 years later. All right. Let's see. So what is this? That's cancel the 3s, the 4s, the 5s, the 6s, and the 7s. This is log 8 divide log 2.
Done,
All right.
huh?
I'll show you guys how to do it. I'm sorry. I'm just messing around. So what I did here, right? You can, if you notice the pattern from the previous problem where we had, well, I'll just show you the first part. I'll show you what I did in my head and then we'll work it out. But this is what I did in my head. So this is using change of base, log 3, log 2. I just right now started doing it with the cursive L and I can't stop myself for some reason. And then this is log 4 divide log 3, right? So these two cancel. So you would get log 4 over log 2, right? So if you just carry that chain down the line where you notice that the 3s cancel, like whatever the argument is, it's canceling the next base. So the 3s would cancel, the 4s would cancel, the 5s would cancel, the 6s would cancel, and then the 7s would cancel. So your last part would just be log 2 or log 8 divided by log 2. But I will show you the whole process. So this is our next one, right? And then our next one in the chain, right? We just did these first two. So our next one is times log 4 of 5. So this is log 5 divide log 4. And these two cancel. So we get log 5 divide log 2. And then our next one in the chain is log 5 or log 5 of 6. So this is log of 6 divide log of 5. And we cancel. Get log 6 divide log 2. Go to the next step in the chain, log 6, 7. So log of 7 divide log 6. And we cancel. Two, and we get to our last step, which is log of 8 divide log 7, and we cancel. So we get log 8 divide log 2, right? Now this step, we'll take it back over here to the beginning. All right, do this, come down here. We got log 8 divide log of 2, reverse the change of base formula, and we'll get log 2 of 8, right? So this is asking what power do we have to raise 2 to in order to get 8? And that is 3. And if you can't, see that directly, because sometimes it can be hard to pull apart what a log is actually asking you. I know I still struggle with it. We could also say, or log base 2 of 2 cubed equals 3. Log base 2 of 2 equals just 3 because this goes to 1. 1 second. Goes to 1. That's another way to look at it. Okay, cool. You want me to keep going?
Yeah, why not?
Okay, cool.
Look
Anybody
how
have
fun
any...
those are.
Yeah, I mean, I don't know. I kind of like solving algebra problems. It's way easier than the stuff I do.
It's a good break, man.
Yeah. But does anybody have any questions on this? And like what I was talking about, how you can kind of see that pattern of going from the base from the argument to the base, from the argument to the base over and over again. Anybody have any questions on that? I'm going to assume that's a no. All right. Hopefully I didn't melt everybody's brains there. Okay. So we're going to take advantage of our addition property to multiply these two together. So we will have log A of square root of x plus square root x minus 1 times square root of x minus 1. Now there's a couple different ways to work this out. This is what I'm noticing here. I know that a minus b times a plus b equals a squared minus b squared. And in this case, I can say a equals the square root of x and b equals the quantity square root of x plus 1, right? So then this becomes the square root of x squared minus x plus square root of x plus 1 squared. And this is equal to
Oop,
x minus the quantity. What am I doing? I need an eraser. There we go. So x minus the quantity, right? X, and then it is plus 1, right? So then this is equal to x minus 1, and this is equal to negative 1.
Oh, yeah, not the same.
Not what it's supposed to be.
Oh, because you changed the sign again.
What I changed? Oh, I made it plus 1. Oh my gosh, guys, I'm so sorry.
Where were you, Pete?
He checked out reasonably
Checked
so.
I was getting my chicken piccata. It was getting cold, so I had to go.
Yeah, he checked out reasonably so. Okay, x minus 1 whole k.
Better.
There we go.
Chicken
so this is
piccata.
minus 1 plus 1. This is just 1, right? Or you could work this all out. So I'll just show you how to do that real quick, right? Square root of x plus x minus 1 times square root of x minus 1. FOIL, right? First is the square root of x times the square root of x. That is the square root of x squared. And then we get the square root of x times negative square root of x minus 1. We get square root of x minus 1 times square root of x. And then we get plus times minus is minus square root of x minus 1 squared. These two terms in the middle are the same with a difference of sign, so they go away. And we're left with x minus x minus 1, which we know equals 1. So this becomes log base a of 1, which we know equals 0 in all circumstances, because that's one of our rules. So there you go. Let me put that up here, work that out. Any questions on that? But you see how much easier this one was if you can just memorize some basic facts like these log rules and just sort of keep them in your head and plug stuff in for them, like how much easier it becomes. I've never regretted doing my homework like this. I know like it's a buzzkill and it's tedious, but it just saves you so much time in the long run. As long as you don't make dumb mistakes and mess up your signs. Okay. So we want to show that the natural log of, I can't answer that right now. The natural log, let me just close that. The natural log of 1 plus e to the 2x is equal to 2x plus the natural log of 1 plus e to the negative 2x. Okay. So I guess what I would start with would be,
Choose a side.
yeah, choose a side and go for it, I guess. I'm going to start with the left side. So we have 2x plus ln 1 plus e to the negative 2x. I want
Ooh.
I want to start with that side. Never mind. I need to get rid of that shit. Okay. So we're going to start with... Did I just break the computer? No. Okay, there we go. All right. So we're starting with ln of 1 plus e to the 2x. Whew. Okay. So I got to get this 2x outside. So what if I exponentiate it? Then I get e to the ln 1 plus e to the 2x, but this is just 1 plus e to the 2x, which don't really help me.
Factor.
Yeah. Okay. So let's make this equal to ln 1 plus e to the x times e to the x. Will that do it? No. No.
You want me to tell you?
Sure, why not?
Factor the e to the 2x out.
So, oh, I see what you're saying. Oh, that's gross. Okay, so check this out. If you take 1 plus e to the 2x and you divide each of these terms, is there a preferred order to break down these types of problems? So if you're splitting apart, I just noticed that. Let me take care of that real quick. So if you're splitting apart something like x plus, not plus, this give you like a, a, a kind of a big example. We got log base m of x, y, z divided by t u v squared, right? If you're starting here, you want to split the division first, right? You can start by separating it according to the multiplication. You just have to be very, very careful about how you do it. But I feel like the easiest way to do this is to start by splitting the division. So you would get log m x, y, z minus log m of tuv squared.
Also,
And then,
Carl, I
Mhm.
think he might have been saying as well as which side should you start on?
Oh, for one of these problems?
So yeah, so that's the fun part. So these are called
Oh,
they're called identities. So
gotcha.
you'd want to choose, usually with identities you choose the more complicated side. But yeah,
Man,
it's all
yeah,
just trial and error.
yeah. But so for breaking down logs in general, I would say always start with your division, and because you don't have to do division first, but it introduces that sign error possibility, and it's just always easier. I feel like one of these days I'll be able to erase this part if the thing doesn't break. You gonna catch up with me? They're like locked up on me. As far as like identities, man, algebraic proofs are always kind of a pain. I guess like you generally want to, I think generally starting with a more complicated side can help, but I would say it's sort of the way that I approach them, and I think most people approach them is you kind of want to like look at the problem and try to like do that whole like play a couple moves ahead thing like with chess, and try to see if you start trying to manipulate some things, like what can you get to try to get closer to one side or the other, right? So like the reason why I started with this 2x plus ln 1 plus, I started with the right side first, is because what I was going to do is like, okay, I know if I can exponentiate these, then maybe I can stick them back together, but that wouldn't have worked out with what I was looking at. Like, I'm sure I could have worked it out eventually, but just looking at the very next step after raising everything here to the power of e would have been gross. I think what Professor Carrillo is saying on this case, starting with the simpler side and then factoring out will work, right? But to get back to this factoring out step, if I divided everything here by e to the 2x, right, then we would get 1 over e to the 2x plus 1, right? And this is equal to e to the negative 2x plus 1. And if I started with this as a quantity, right, 1 plus e to the 2x, and I factored this e to the negative 2x out, right, then this is the same thing as saying e to the negative 2x times e to the 2x, or sorry, not negative 2x.
E to the positive 2x
Yeah,
times.
e to the positive 2x, e to
Yeah.
the positive 2x times e to the negative 2x plus 1. And this is what Professor Carrillo is saying. So we can make this problem up here e to the 2x times e to the negative 2x plus 1. We can split this using the addition rule. We get ln e to the 2x plus ln of e to the negative 2x plus 1. We use our power rule to bring this down as 2x. We'll have ln e left over. That's just 1 plus ln. If we reverse this order, right, because it's just addition, we can turn it around, plus e to the negative 2x, and you're done. Yeah, so that's like way easier. The way I was going to go with it, which I could maybe eventually figure out, but would have been a pain, I was going to do e to the 2x plus e to the ln 1 plus e to the negative 2x. So this is, or actually, sorry, you can't do it like this. You have to, like this. So this is e to the 2x, e to the ln 1 plus e to the negative 2x. So this is e to the 2x times 1 plus e to the negative 2x. And then from here, this is where, like, in my head where I got stuck, like, where am I going to go
Yeah.
from here? And it's like, I guess what I could do is I would multiply these together, right? And you would have gotten e to the 2x plus 1, but this is not ln. So that's where I got stuck, is I could get back to this, but I didn't have the natural log in there. So anyway,
Just had to factor it out, and that was it, right?
yeah, real simple to see that.
Yeah, that's it.
Well, whenever this catches up and it deletes. There we go. I'm like making this thing chug. Okay.
Dun, dun, dun. All right, last one.
Yeah, we're almost done here. Let's
Thank-
do
Thank
pink,
goodness.
right? Okay. If f of x equals log base a of x, show that f of 1 over x equals negative f of x. Okay, well, that's not that hard, right? So,
No, yeah, just plug in
yeah.
1 over x.
yeah.
That's
So
it.
we have f of x is going to equal log base a of x. So this naturally gives us f of 1 over x will equal log base a of 1 over x, right? We follow our, or I want to convert this first to x to the negative 1, right? We want to pull out our
Exponent.
power, our exponent. My brain is stopping. Log base a of x, and look at that. This equals negative f of x, and we're done.
Yay!
That's that.
Now, was that too extra?
Yeah. especially this problem. That one
Yeah.
was like, that one tripped me up. You want to get used to being able to see these sorts of weird, wonky substitutions like this, though, because this is one of those, like when I talk about calculus, like what stops you in calculus is in algebra. A lot of simplifying derivatives is being able to readily catch things like how do I factor out something to give me the form of something I'm looking for, you know?
Yep. It's the killer, man. But
It really is.
okay. Well, those are logarithms. Of course, more to come next class, but we're done.